are good. Yeah. Taylor's proposition. All functions f of x can be approximated by a polynomial p of x. Period. End of story. Do you believe that proposition to be true? All functions, has to be a function, okay, so pass the vertical line test, could be approximated by some polynomial that would match up to that function.
I'm guessing yes. We'll be teaching about this.
Okay. How complicated do you think the polynomial has to be?
Simple.
Okay. All right. So let's start small. All right, this doesn't count as an example, it's just an intro. Okay, consider a function to be the natural log of x minus 1.
Of course you start there.
Okay, also consider a polynomial to be the simple linear function x minus 2. All right, these two things share a common point. Okay, the common point that they share is 2, 0. Both of them have 2, 0 in common. All right, let's get a visual. Okay, the natural log of x minus 1 is shifted in what direction?
Right.
Okay, and so it's going to look like this. Okay, x minus 2 is a line that is shifted 2 down. Okay, we call that a tangent line. We call that a linear approximation. Okay, at their point of tangency, okay, I'm going to zoom way in, at their point of tangency, okay, yeah, on your paper, okay, these two things match up really nicely. Maybe from like here to about right there. Okay, then they start to separate a little bit. Okay, why do they separate? Well, because the linear line has a constant slope, and the natural log is concave down, which is pulling its slope away. Okay, so what we say is that we say that f of x, which is the curve that has slope and tangent and a concavity, is approximately equal to p of x within a small domain. All right, well, how do you widen the domain that those two things match up for? What do you have to make your polynomial? Right now my polynomial is linear. I got to make my polynomial curved, right? And it's got to match not only the slope, but what else does it need to match? The concavity. Okay, I want to match the slope and the concavity. All right, so if P1 of x was x minus 2 that we just did, okay, P2 would be a parabola. That parabola, it'll match the slope and the concavity for a little bit, and the parabola is x minus 2 minus half of x minus 2 squared. I'll tell you how I came up with that in just a minute. that parabola matches at the same point. I'll do a different color. Okay, it comes up and it matches the slope and the concavity for longer. But eventually the parabola is going to have a negative slope and the natural log stays with a positive slope. So this widens the interval that they converge on each other, makes it more. Okay, but it eventually falls apart. Okay, I would build another one. Okay, what if I could make a cubic? Okay, the cubic is going to be x minus 2 minus half x minus 2.
So we just add it on?
Yeah, I'm going to tell you how, and there's a specific pattern way that you do that. Okay, cubed. Oh yeah, thank you. And you could probably guess, at least for this problem, what this pattern is going to do. Well, that's going to create a cubic, and that will widen the interval of convergence even further. You could create a 4th degree and a 5th degree, and you just keep going. These are called Taylor polynomials. Yes? I will teach you why it's not. Okay? Okay, it is not. Okay, P4. You could probably follow the pattern for this. It's going to be squared plus a third x minus 2 cubed minus a 4th of x minus 2 to the 4th. And that would, again, approximate it even closer. So we're all about creating a polynomial that more closely matches the original function with a wider and wider and wider domain as we go. Okay, that is Taylor's proposition and his method of creating these polynomials. Okay, so that's the basic idea. And then we're just going to teach you how to create these polynomials as they widen their domain of their interval of convergence. This is all credited to Taylor. That's what we're going to work on today. All right, here we go. Okay.
That's just the one I basically.
Go. Building Taylor polynomials uses derivatives and factorials to create the coefficients. The length of it is called its order. Okay, so first order is like linear. Second order, quadratic. Third order, cubic. Fourth order, etc. Okay. All right, yes?
So if the polynomial for natural log goes on forever, does that mean the order of natural log is infinity?
No, it's not the order of the natural log, the order of the Taylor polynomial that you create. Okay? The higher the order, the more accurate it will be. Okay? So the coefficients are like this. We'll call the coefficients C sub n. Every coefficient is created with the following. Okay, f n of x of a, I think would be better. Why is it not writing a? Over n factorial. All right, so the first coefficient is called coefficient 0, or c sub 0. That would be f, and we don't usually write 0 there, but that means order 0. And if it's order 0, it's going to be a constant, right? So we typically don't write that. We just write f of a over 0 factorial. What is 0 factorial, everybody? 1. All right, the second coefficient, which would be called C1, is going to be f prime of a over 1 factorial. It's a prime, yeah.
Is it one or prime?
It's a prime. Okay, what's 1 factorial? 1. What's factorial? The numbers from 1 to that number multiplied together, but 0 is the only one that's defined as 1. So 0 factorial and 1 factorial are both 1. So then 2 factorial would be 1 times 2, which is 2. But 3 factorial is 1 times 2 times 3, which would be, yeah, but we'll get there. That's just the definition. Okay. All right. 2. That would be f second, okay, over 2 factorial. And then we just keep going.
So is there like a hint to that? Because like for that example you did, you just kind of like added on, like there's like 1/2.
Yep. So now we're going to show how to build a Taylor polynomial. Any nth Taylor polynomial is going to start this way. Yes, sir.
The first term is C0.
It's like, yeah, it's like n always starts with 0. We start with the 0th.
Or it's kind of like
It's-
zero index.
Yeah, it's not. It's the it's like, you know, initial velocity, and they do v sub 0. It's the initial term.
Okay.
All right. So we will have the initial term times x minus a to the 0. Then plus the next coefficient times x minus a to the first. And then the next coefficient times x minus a to the second, etc., etc. So it will be any n coefficient times x minus a to the n. That is how a Taylor polynomial is built. It is really helpful to find all your coefficients first and then slot them into the polynomial. So depending on what polynomial order they ask you to do, you know how many you need. Okay. Let's start fairly without we having to do a ton of work. Okay. Create P4 centered at a equals 0, which is basically the point of tangency. Using the following. F prime, F double prime, F triple prime, F fourth. I'm just going to tell you what the numbers are. We're just going to build it for practice. 5, 7, 11, 13, 17. Okay, now let's find our coefficients. So I would say let's find our coefficients C0, C1, C2, C3, C4. All right, the first coefficient takes the original f and divides by 0 factorial. The second coefficient takes the derivative 7 and divides by 1 factorial. And then 11 divided by 2 factorial. 13 divided by 3 factorial. 17 divided by 4 factorial. So now we're ready to build our polynomial now that we have all of our coefficients. So P sub 4, the fourth order polynomial. Okay, what is 5 divided by 0 factorial? Okay, times x minus 0, which is where this problem is tangent, centered at, to the 0. Next one, 7 divided by 1 factorial is 7. X minus 0 to the first. 11 over 2 factorial is 11 over 2. X minus 0 squared. Okay, 13 over 3 factorial, that's 13 over what? 6 times x minus 0 cubed. And the last one is 17 over, very good, 24 is 4 factorial, times x minus 0 to the fourth. So let's simplify and clean that up a little bit. So we'd have 5 plus 7x plus 11 halves x squared plus 13 sixths is x cubed plus 17 24ths x to the fourth. That quartic fourth order polynomial will match the mystery function, which I did not give you, I just started you with a table, very accurately within an interval of convergence that's wider than it would have been if it was a cubic or a quadratic or a linear. Okay, that's how you basically create that. Now I gave you it was easy because I gave you 5, 7, 11, 13, 17 to start with. Okay, usually you're going to have to figure those out on your own. So that's what we're going to do right now. Okay, we're going to figure those out by ourselves. That was the first. Okay. All right, create P7. Don't worry, don't worry, don't worry. Okay. You're like 7? We have to do 7? Okay, to model f of x equals sine of x. To model sine of x centered at 0. Yes, we love 0. Okay, I mean, this really is, I'm creating a polynomial that's going to look like sine. Okay? For a while. But it's going to all match up with sine. And it's going to be a 7th order, so it's going to be something to the 7th.
Maybe a line following program, but like you're like following the line to like once it hits the left, it like turns.
Yeah,
and
or
goes around
all these
the
adjustments. Yes, ma'am.
Will it always give you the egg?
Yeah. Okay, so it helps me to just kind of figure out my derivatives and figure out my coefficients, and then I build my thing. Okay, that's sort of how I go. So I'm going to need to do f prime, f double prime, f triple prime, f4, f5, f6, and f7. Okay. So I am plugging 0 into f, and then f prime, and then f double prime, etc. Okay, so plug 0 into f.
0.
Great. Plug 0 into f prime. Thank you, because what is f prime? Cosine, and 0 into cosine is 1. Plug 0 into f double prime, which is negative sine, so back to 0. Plug 0 into f triple prime. Negative. And as follows. I told you it was going to be okay. Okay, so then my coefficients well, a bunch of them are going to be 0. The odd ones, okay, so it would be 1 over 1 factorial. The third one would be negative 1 over 3 factorial. The fifth one would be positive 1 over 5 factorial. The seventh one would be negative 1 over 7 factorial. So my 7th order polynomial is 0. Should I be really specific? Do you want me to write x minus 0? No, am I okay? You guys gonna? All right. 0 plus 1, and then that would be x times 0 to the first. We love it when it's centered at 0. It's so great. All right, then plus 0 again. Then minus how much? 1/6. And that'll be x minus 0 to the third. And then plus 0. And then plus 1 over, what's 5 factorial? It is. It's 120. Okay. That would be x minus 0 to the fifth plus 0 minus 1 over, okay, now you need 7 factorial. You know there is a factorial button on your calculator?
Yeah.
Okay, it's under math. So 7 math factorial. Okay. 5040.
He got it.
Because he just multiplied 120 times 6, which is 720, and then he minus 720 times 7.
Oh my gosh, that's so good.
You should probably know up to like 5, like by memory. Maybe 6 is 6 times 12, that's 720, so you should be able to get. Okay, so then if we just clean this up, the 7th order polynomial should be x minus a 6th of x cubed plus a 20th of x to the 5th minus 1/50/40th x to the 7th. That polynomial, if you graph it, is going to look like sine. Shall we try?
Yeah.
Shall we try? Okay.
Oh my gosh, please don't.
Let's do.
Can we do a piece of
All right. This I think could be our last one.
we can't see it.
Oh yeah. I always forget that part.
So how long will our homework take?
5 hours.
Depends on
I'm guessing 40.
how quick you are at like derivatives and stuff.
So 5 hours.
All right. So let's do. Yeah, on day 1, I think most of them are centered at 0, so that's going to help you out. All right. So given, yeah, there's the day 2. Okay, natural log of 1 plus x. We did x minus 1 earlier, so we're doing 1 plus x now. And let's do find P4, 4th order at 0, centered at 0. All right, I can't do these in my head quite as fast as I could do sine and cosine, so it may help you to actually write down what the derivatives are to keep track of everything. So I'm going to actually write down that it's 1 plus x, natural log of 1 plus x is my function. And then I'm going to actually write the algebra down, or of the functions down of the derivatives. So f prime would be 1 over 1 plus x because that's the derivative of natural log. Okay, what's the derivative of that? Negative 1 over 1 plus x quantity squared. And then the derivative of that is negative 2, positive 2 times 1 plus x to the third. And then negative 6 over 1 plus x to the fourth. So it helps me for some of these other, ooh, that was bad, to write those down and then figure out. Now I'm going to plug 0 into all of those to get my values. So plugging 0 into the first one, okay, well I get the natural log of 1. And I plug 0 into the next one and I get 1. And I plug 0 into the next one and I get negative 1. And I plug 0 into the next one and I get 2. And I plug 0 into the last one and I get negative 6. So then my coefficients for my polynomial are going to take those derivative values and divide them by the factorial. So I'm going to get 0. I'm going to get 1 over 1 factorial, negative 1 over 2 factorial, 2 over 3 factorial, and negative 6 over 4 factorial. And some of those can be simplified. So then I'm ready to build my polynomial, my fourth order Taylor polynomial. So this will be 0 plus 1 times x minus 0 to the first minus half of x minus 0 squared. What is 2 over 3 factorial? 1/3. Okay, and then what about negative 6 over 4 factorial? Negative 1/4. See how the fractions are forming?
Okay.
Okay.
We're sure it should be 1 too.
All right, so we ended up with x minus a half of x squared plus a third of x cubed minus a fourth of x to the fourth. Right, that fourth order polynomial will resemble the natural log of 1 plus x within a certain interval of convergence, where those two will be the same. The longer you make the polynomial, the more they will overlap and be accurate with each other.